Ladies and gentlemen, class recording has started. So, today there are some pictures and some problems up here that I'm going to show you on the board that we're going to talk through. Some of them are review of some things we've done so far. Some of them are some introducing of new topics that we did yesterday. Like I said, I forgot to get these pictures copied. I will get them copied tonight and I will get them to you tomorrow. But today, if you would like to write some things down, make some notes, jot some pictures, that's up to you. Alright? Alright, for starters, let's go with this question right here. What happens to electric potential energy in this situation and why? Discuss with the person next to you. Go.
Alright, so the next one that we're going to make is a parallel circuit. It has two switches. One switch is on the outside, one switch will be in one of the parallels. Does that make sense? Okay. We'll read this one first. Right?
Hey, will you do something? Will you replace that switch with the other switch?
Which one?
Is there a second switch there?
I thought there was.
Yeah.
Okay. Replace, because that one has like an actual
Yeah, that's
slider
actually cool.
switch, you know what I'm saying, instead of just pushing it. So.
Well, that's way easier.
All right, let's discuss. So, first, what happens to electric potential energy in this situation? Ryan? Okay. Electric potential energy increases because a positive charge is being pushed closer to another positive charge. Let's talk about this part down here at the bottom. This hand, this arrow, and this letter F. Why is that included in this picture? Right, good. Okay, force is acting on the positive charge. Will this happen on its own? These positive charges won't come closer together. We talked about that there's only one way to make that happen. What has to happen in order for these two positives to get closer together? Work has to be done, right? This is an increase in energy. The only way energy increases is if work is done. What's one of the things that we need in order to do work? A force, right? And that's why that force is there. That force is showing that work is being done in order to increase the electric potential energy. Good? Okay. Next picture looks like this. Which object, A or B, has more electric potential energy? Why? Discuss with the person next to you. Go. A or B? They're just like something's like You know what, Joseph? It makes it more clear in your head. Picture them as round, okay? Or if you draw like a picture of it, you can draw them round. That's fine. Okay. All right. So let's discuss which object, A or B, has more electric potential energy. B has more electric potential energy, right? We talked about that there are two ways to increase electric potential energy. One, go ahead. You can change the strength of the electric field. More positive charges means stronger electric field, right? So B is going to have more electric potential energy than A, even though they're the same distance from the blue object. Because the electric fields are stronger for B than they are for A, that's going to be more electric potential energy for B than A. Okay? Good there? All right. Next, let's start reviewing some of the circuit ideas that we talked about yesterday. So, we talked about a circuit yesterday, right? And we said, well, let's define a circuit. What's our definition of a circuit? You can look at your outline from yesterday. So So what is our definition of a circuit? Jules, go ahead. A set of components that provide a complete path for the movement of charge. Okay? There are two things that we have to have in order for there to be a circuit. What two things do we have to have? What's one, Stephen?
Power source.
A power source, or if we want to talk about, use our vocabulary, a battery is a specific type of a voltage source, right? We said voltage relates to energy. So we have to have an energy, our power source, but more, using our vocab as a voltage source, right? And then the other thing, well, it doesn't necessarily have to be a switch, but getting back to the definition, a switch can make the path either a full path or a non-full path, right? So it has to be a complete path. Right? If there's no complete path for the charges to flow, they won't.
So it's a closed circuit.
A closed circuit, okay? With that in mind, here are pictures of 7 simple circuits. 3 questions. How many closed circuits are there? How many open circuits are there? How many short circuits are there? So, there are 3 components in here, right? These are batteries. These are light bulbs, right? A light bulb has a conducting part, the metal part down at the bottom, and the glass part at the top isn't conducting, and then the lines are just wires, right? So those are conductors. So batteries, light bulbs, wires. How many closed, how many open, how many short? Discuss with the person next to you. Go.
There's 1, 2, 4 closed.
I'm just labeling them so we don't talk about it. Fifteen seconds. 15 seconds. All right. Let's discuss. So, closed circuit. Let's talk about our closed circuits first. Closed circuits have to have voltage source and they have to have a complete path. Get from one side of the voltage source to the other side of the voltage source, right? There are 3 closed circuits. They are B, C, and F. Okay? Good, Lauren. Okay? Hold on for E for a second. Okay? We'll talk about E in just a second. Can you tell us which one that one's going to be? Actually, hold on. We can jump straight to E. So what were you going to ask about E? Go ahead.
Because like the one wire goes from one end of the wire to another, which is making it closer, but then the one that connects to it goes.
Okay. So Lauren said that we have this wire that goes from one end to the other, right? Okay. But then we have this wire that doesn't. Okay? So, is there a complete path to get from one side of the battery to the other side of the battery?
Yes.
There is. The purple path is. Okay? It's not connected to the light bulb. So will the light bulb be lit here? No. Okay. That makes the light bulb adds resistance to the flow of electrons through the path. If there's no light bulb, what's the resistance like? Well, let's not go with no resistance. How about if we go with very low resistance, which is a characteristic of what? A short circuit. E is the short circuit because it provides a complete path to get from one side of the battery to the other, but it's only a wire. There's very low resistance in this path, and as a result, there is a very high what? If there's very low resistance,
Voltage.
there's a very high current. And if there's a lot of current, that means there's a lot of electrons. And if there's a lot of electrons, they move very, very fast, and they get hot. Okay? Say again? It's heat. This creates heat because in a case like B and C, the electric potential energy that the charges are gaining out of the battery, they are turning into light. But here, the only thing that they turn that electric potential energy into is heat. You can do that at home. You can take a paper clip and put it to two sides of the battery. It'll get hot really, really fast. Right? I don't recommend you try it, especially because if you hold the paper clip with your fingers on both sides of the battery, it'll burn your fingers. Right? But it also can burn like a piece of paper or something like that. That's a short circuit. Very low resistance, very high current, it gets hot. That good.
So is that like why light bulbs get hot?
So, Pat said, is that why light bulbs get hot? Actually, light bulbs get hot because the resistance of that light bulb causes heat, which then lights things up. So yeah, light bulbs are actually turning electric potential energy into heat and light, whereas a short circuit is just going straight to heat. Okay? That being said, just to wrap up this problem, A, D, and G would be the open circuits because there is no complete path to get from one side of the battery to the other. It's pretty obvious in A and G, right, because there's no wire attached to the bottom of the battery. But in D, the wire is attached up here to the top of the light bulb, but the top of the light bulb is made out of what? Glass, and glass isn't a conductor.
It's an insulator.
It's an insulator. All right. Good there? Sure. Let's talk. Well, let's go to the next thing. Okay. All right. So I'm going to show some things up here on the board with the camera. I'm going to actually stop the recording because this is like a streaming thing and it just makes the recording a really, really big file. So if you're watching this later on, you won't get to see this part, but we'll review what we're talking about later on. Okay? All right. All right, everybody, recording is started again. Let's talk about the next two questions. Oh, I should unzoom so you guys can see the whole picture. Okay? All right, two questions. How can you describe this circuit? How many light bulbs would be lit? Discuss with the person next to you. Go.
What?
They would not be lit.
Yeah, it wouldn't be lit.
Yeah.
It's behind the path.
All right, why don't you guys go go sit down?
Is this fun?
Fine, let's go.
Thanks for your help.
Can we take it with us?
No, because it's not my kid. So
Should we just
I'm
clean-
borrowing it from somebody. So.
Should we clean it up?
No, that's okay. I'll clean it up after class. So. All right. So I would say that there are there are two words that we could use to describe this circuit. Lauren, what's one word we could use to describe this circuit? Open. What's the other way we could describe this circuit? Rachel, go ahead. Series. Okay, it's an open series circuit. And because of that, how many light bulbs would be lit here? 0. There is no complete path for electrons to flow through any of those light bulbs. Okay? Next picture. Discuss with the person next to you. Go.
It tells you when to
That determines how much current is going to flow through. No, this question. Now, Jules, what it would matter for if this battery was a lower voltage, let's say we made it a 6-volt battery, what would happen to the lights? They wouldn't be as bright. Yeah. Yeah. All right. So I would say that there's probably only one word that we could use to describe this circuit. This would be what kind of a circuit? This is a parallel. It's hard to say that it's an open parallel circuit because some sections have current flowing and some sections don't. So I would say that this probably parallels the best we could do. And how many light bulbs would be lit in this picture? 2. Right? The top 2 would be lit because they have complete paths for electrons to get from one side of the battery to the other, but the bottom one would not. Okay? All right, good with this?
Yes.
Okay, next picture. Discuss with the person next to you. Go.
Where's the battery?
Let's say they're connected to a battery, just not in the picture.
Oh, A
This
does.
one is well, we're just
It's series and they would have the
I think A does but you know that's the bottom is across there.
All right, let's discuss. Hey.
It's cute.
All right. So the difference here, well, what is the difference between path A and path B? Brian, go ahead. So in A, there's only one path, but in B, there's 2 paths. So Ryan, we could describe them using vocab words, right? How are these resistors connected in A? Somebody else want to help them out? If there's only one path, what do we call that? Series. So we say these resistors are connected in series, whereas these resistors are connected in parallel. Right? So, parallel resistors give more paths for electrons to flow. Like we used the analogy yesterday, it's like opening up more cash registers at the grocery store, right? If there's more paths for them to flow, more current goes through, okay? If there's only one path for them to flow, the more things you put in their way, the greater the resistance is. So the short answer to this question is, which path has the greatest resistance? A has the greatest resistance, okay? Now, let's talk about, okay, so as far as the answer to this question goes, right? Come on, pen, there we go. A has the greatest resistance. Let's talk about something that we introduced yesterday, but we didn't quite get all the way through it. And that's the idea of equivalent resistance. All right. In series, what happens to the resistance as we add resistors? It gets greater, right? The more resistors we add, the greater the resistance. And it's a very simple linear relationship. So in series, the equivalent resistance, R with a subscript EQ for equivalence, okay, is just equal to R1 plus R2. So in this case, what would be the equivalent resistance of path A? 16 ohms, okay? Meaning, we could take these two 8-ohm resistors out and replace them with one 16-ohm resistor, and we would get the same current. Okay? Good there. Yeah, it would be a bigger light bulb or a brighter light bulb, right? Or just a bigger, more resistance to flow through there. Okay? Now, go ahead, Joseph. So that's so the question is, the amount of resistor doesn't matter, it's just the same amount of resistance. Technically, yeah, that's what the idea of equivalent resistance is. The equivalent resistance is, okay, what is like the total resistance here, all right? The total resistance is 16 ohms, even though it's split up into two 8-ohm resistors. If we had four 4-ohm resistors, it'd be the same equivalent resistance. Because in series, even though there's 4-ohm resistors, each resistor isn't as strong. All the charges would still have to go through all 4 of them. Does that make sense? So whether you have two 8-ohm resistors or four 4-ohm resistors or one 16-ohm resistor, it's still the same. Does that make sense? Okay. In general, though, let's switch to parallel. In general, the more resistors that we add, what does that do to the resistance overall? In parallel, if we add more paths for charge to flow, the total resistance decreases. So equivalent resistance increases in series, but decreases in parallel. More paths, less resistance. Okay? Good there? Now, let's talk about how we mathematically do it. So, equivalent resistance in parallel is a little different. It looks like this. And we didn't actually write this down. It's on the back of your outline from yesterday. So if you want to flip it to the back of your outline, it would look like this. Okay? So if you look at the back of your outline yesterday, 1 over REQ equals 1 over R1 plus 1 over R2, and you would just keep going no matter how many resistors you had. Up here on the board, I only have 2 resistors, so I'm going to stop right there. Okay? But if you had more resistors, you would just keep adding them in that fashion. Okay? So let's apply this equation to these 2 resistors in parallel. Okay? Hold on one second. So, we're trying to find REQ. That's our unknown in this problem, right? Resistor 1 is how many ohms? 8. So we go 1 over 8. Plus resistor 2, which is also 1 over 8. Okay? Right-hand side, we're adding fractions together. They have the same denominator, so we can do that, right? So this equation now becomes, and it looks like this. Okay? Does that make sense? 1 over R equals 2 over 8, yes? But we need to solve this equation for R. So what are we going to have to do? We can cross multiply this. Hold on. So we can cross multiply. Hey, still like 5 minutes left.
Is he done? No, 2R equals 8.
So if you solved this equation right here for R, you would get 4 ohms. Okay? Does that make sense?
So you'd have So would you just get rid of one of them and you're like,
What we're saying is, so going back to, hey, getting back to this idea of equivalent resistance. Saying that the equivalent resistance of these two is 4 ohms would be saying we could take these two 8 ohm resistors out, replace them with one 4 ohm resistor, and it would still have the same current through like the entire part of that circuit. Okay? Jules, go ahead. Okay. Yeah, if the numbers weren't the same, you know, you would do like some fractions and, you know, make them common denominators and stuff like that. It gets a little bit more complex mathematically, but the idea is the same. Yeah, it's okay. Yeah, we can make it as a fraction. Jules, when I'm giving you stuff on on a test or on a worksheet or something like that, I'm going to give you numbers that come out nice and even, because I don't want you to do that. You know, so. Not good.
Like 3 resistors. It's like, say that it's all 8.
Yep.
But then you would go and 1 over R equals 3. Oh, wait, no.
And then just solve it for R. And then it becomes a decimal, right? But it's a smaller decimal then. Right?
I want to do
All right, hey, tomorrow we are going to the library, but come here first. Then we'll go down together. Everybody, class officially ended, but I wanted to finish up these last 2 slides here just so we had a full recording of the rest of the slides here. So the next slide that comes about is this one, and it says, what is the equivalent resistance? So here we have resistors connected in both series and parallel. So we're going to start off finding the equivalent resistance of this section to begin, because these two are in parallel. So like we said, if I was going to do this, too far. So the first thing we do here when we have resistance in series and in parallel, find the equivalent resistance of this section. So like we just discussed, in parallel, the equivalent resistance is equal to this expression. 1 over Req, which is the equivalent resistance, is equal to 1 over R1 plus 1 over R2. In this case, both of our resistors are 8. So we go here, and we go 1 over 8 plus 1 over 8, right? Solve that like this. And we find that the equivalent resistance here is 4 ohms. Okay? Remember, resistance in parallel, we solve, equivalent resistance in parallel, we solve with this equation. And on the next screen here, that's basically what they did. So here, we replaced this entire section, actually I should do this. We replaced this entire section with this one equivalent resistor. Now, the 8 and the 4 are in series, so when we add them up, we get a total equivalent resistance for this section of 12 ohms. Okay? The next picture looks like this. Which path would have the greater current, top or bottom? Now, in my second period class, we got this far, and we discussed that there is actually a correct answer here, is that neither one of these paths, the top or the bottom, would have current, because in this picture there is no voltage source. So technically you would say that neither one of them has current because there's no voltage source in this picture. But let's say that they are connected to a voltage source, and if that's the case, which one would have the greater current, top or bottom? Well, just like we did in the last problem, first thing we should do is find the equivalent resistance of those two resistors in parallel. So, like we just discussed, to find the equivalent resistance here, 1 over Req is 1 over R1 plus 1 over R2. In this case, both of these resistors that are connected in parallel are both 2 ohms. So we'd substitute in like that. Then, and solving this equation here, the equivalent resistance of this little section in parallel is 1 ohm. And so, right, that's what they did here in this graphic, replacing this section, these 2 resistors in parallel, with that one equivalent resistor of 1 ohm. Now, these 2 resistors are in series. We have this 2 ohm resistor, that 1 ohm resistor, those are in series, so we add them together and find the equivalent resistance of the top path is 3 ohms. Great. The bottom path is also 3 ohms. That being the case, both of those paths would have the same current if they were attached to the same voltage source. So I just wanted to finish those 2 things up because that's how far the second period class got today. We will definitely, like I said, we will definitely look at some of these things a little bit more when you do your virtual circuits lab in the library on Thursday and Friday.